Hello and welcome to Tvaritam.AI. In this video, we will understand decision trees. A decision tree is a flowchart-like model that learns a series of yes or no questions about your features and maps them to an output. It starts at a root node, splits the data into internal nodes based on feature values, and finally reaches leaf nodes that produce the prediction. One of the biggest advantages of a decision tree is that they are completely interpretable. You can actually trace the path from the root to a leaf and understand how a decision was made, which reduces the need for manual reasoning. Now, decision trees can be used for both classification and regression. In classification, the output is a class label. The model uses splits like Gini impurity or entropy to reduce uncertainty, and at the leaf node, the output is simply the majority class. For example, if most values in a node are yes, then the prediction for that node will be yes. In regression, the output is a continuous value. Here we use metrics like mean squared error or mean absolute error. At the leaf node, the prediction is the mean of the values present in that node. So if a node contains values like 30, 40 and 50, the output would be their average, which is 40. Next, we will discuss the split criteria. The idea here is to split the data so that the split makes it more organized, more predictable and easier to model. Therefore, a split criteria measures how good a split is by checking whether it reduces impurity in case of classification or error in case of regression. In classification problems, the goal is to make each node as pure as possible, meaning it contains data points mostly from a single class. The common approach for this is to use Gini impurity or entropy. In Gini impurity, the idea is that if we randomly pick a data point here, how likely are we to classify it incorrectly? Higher Gini means more mixed classes indicating a worse node, while a lower Gini means more pure classes indicating a better node. So the tree chooses split that reduces Gini impurity the most. Entropy on the other hand comes from information theory and measures uncertainty. High entropy indicates high randomness or mixed classes, while low entropy indicates high certainty or a pure node. Now while making a split, we often use information gain, which is reduction in entropy after the split. So the tree asks which split reduces uncertainty the most. Now looking at this example, we have a small dataset with a 50-50 split for our target variable. 4 instances of approved and 4 instances of rejected. Here the Gini value is highest at 0.5. Now when we use income to create a split, we have 3 nodes: low, medium and high. Low and medium give us pure nodes, so the Gini here is 0. While medium again has a 50-50 split with a Gini value of 0.5. When we calculate weighted Gini values for all 3 nodes post split, we get 0.125 and information gain is thus 0.5 minus 0.125, that equals to 0.375. Now here again we can see 2 similar trees for the same dataset. But in the second tree we use employed as our root node, and the Gini gain is 0.125 as compared to 0.375 when we used income. So the split made by income is better split as it provides more information gain. In terms of comparison, Gini is faster to compute because it doesn't involve logarithms, while entropy may produce slightly more balanced splits. But in practice, both usually result in similar trees. As displayed on the graph here, the values for both Gini and entropy are minimum at 0 and 1 and maximum at 0.5. Now for regression, we are not predicting categories anymore. Here we are predicting continuous numbers. So instead of purity, we focus on how close predictions are to the actual values. For regression, commonly used split criteria include mean squared error and mean absolute error. Mean squared error measures the average square difference between actual and predicted values. It tries to minimize variance within each node. Squaring means that large errors are heavily penalized. So the tree prefers splits where data points in each node are close to each other, while big mistakes are avoided aggressively. Mean absolute error measures the average absolute difference. It does not square errors but treats all errors more evenly. This makes it more robust to outliers. It is useful when we don't want extreme values to dominate the model, but it can be slightly harder or slower to optimize. Now in this example, where we see house price as a target variable, each node predicts the mean of its samples. Here, the tree tries every feature and threshold, then computes the weighted child mean squared error and picks the split that gives us the highest variance reduction. In this case, the root node itself has a mean squared error value of 1150. While after the first split, the weighted mean squared error value becomes 47, thus providing us with a gain of 1003. Now let us talk about regularization in decision trees. Regularization is used to prevent overfitting in our machine learning model. Decision trees can easily become very complex. If we allow them to grow without any restriction, they keep splitting until they almost memorize the training data. This leads to overfitting, where the model performs very well on training data but poorly on unseen or testing data. Pruning is the process of reducing the complexity of the tree so that it generalizes better. In simple terms, we are removing unnecessary splits that do not add meaningful predictive power. When it comes to pruning, there are two different approaches, pre-pruning and post-pruning. In pre-pruning, we stop the tree from growing beyond a certain point. This means we introduce constraints during training itself, like limiting the depth of the tree or requiring a minimum number of samples before making a split. In post-pruning, we first allow the tree to grow fully even if it overfits, and then we go back and remove branches that do not improve performance on validation data, so we essentially cut back the tree after it has grown. In practice, pre-pruning is computationally simpler, but post-pruning can sometimes give better results. Now we will discuss some key hyperparameters used in pre-pruning. These hyperparameters are optional and either one of them or multiple can be used in conjunction. The first one in our list of hyperparameters is maximum depth. As the depth of the tree increases, the training error keeps decreasing. But after a certain point, the validation error starts increasing, which is a clear sign of overfitting. So we usually choose a depth where both training and validation errors are reasonably low. Shallow trees are simple and interpretable, but they may underfit. Medium depth trees, typically between 6 to 12, offer a good balance. Deep trees can capture complex patterns but tend to overfit, especially if not regularized. Completely unbounded trees should generally be avoided on a single decision tree algorithm. In node split controls, we have minimum sample split and minimum sample sleeve. Minimum sample split controls the minimum number of samples required to split a node. If we increase this value, the tree makes fewer splits, which leads to a simpler model. Minimum sample sleeve defines the minimum number of samples required in a leaf node. It is actually a stronger form of regularization because it directly controls how small the final nodes can be. Typically, values between 5 and 15 works well. A useful rule of thumb to avoid any contradictions is that minimum sample split should be at least twice the minimum sample sleeve. For leaf control hyperparameters, we have maximum leaf nodes and minimum impurity decrease. Maximum leaf nodes limits the number of leaves in the tree. Fewer leaves makes the model more interpretable, while more leaves increases the flexibility. Minimum impurity decrease means a split will only happen if it reduces impurity by at least a certain threshold. If the improvement is too small, the split is simply not allowed. Now moving forward with evaluation metrics. Evaluation metrics, unlike the split criteria, are used after training to measure how well the model is performing on the unseen data. For classification metrics, the most basic one is accuracy, which tells us the overall correctness of the model. But accuracy can be misleading, especially in imbalanced dataset. For example, if 95% of the data belongs to one class, a model predicting only that class will still achieve a 95% accuracy. Hence, for most real-world cases, we apply more detailed metrics such as precision. Precision tells us out of all points predicted as positive, how many are actually positive. So it is true positives divided by the sum of true positives and false positives. Recall tells us out of all points predicted as positive, how many are actually positive. So it is true positives divided by a sum of true positives plus false negatives. Last is F1 score, which is a harmonic mean of precision and recall. It gives a balance between precision and recall and is especially useful when you need a trade-off between the two. Now for regression metrics, we have mean squared error, which squares the error. This makes it more sensitive to large errors, so it penalizes them more heavily. We have mean absolute error, which is the average absolute difference between predicted and actual values. It is easy to interpret because it is in the same unit as the target. And finally, we have the R squared, also known as the coefficient of determination. It measures how well the model explains the variance in the data. A value of 1 means perfect prediction, while a value of 0 means the model is no better than simply predicting the mean. Negative values indicate that the model is performing worse than simply predicting the mean value. Thank you.